In this video, I want to talk about determining which direction is up on a surface plot. So let's say that we have this kind of surface plot. So we have x and y, and we say that the z is actually a function of x and y, like that. And then what we do is we just plot f of xy on the z-axis for any point x and y. And the result is this kind of surface plot. Now, on any point on the surface plot, you can say, well, at this point, if you want to go uphill as much as possible, you would go, well, maybe in this direction, something like that. Of course, it's hard to draw a 3D direction in 2D. So the question now is, okay, so which way is this vector pointing? So, okay, how do we determine that? Well, we know that in order to increase f of xy as much as possible at the point xy, we need to follow the gradient. So what does it mean? It means that if we're now at a point xy, like that, then the best that we can do is we can say, okay, we need to move this a little bit in the direction of the gradient. So in the direction df by dx at xy, df by dy at xy. So that's what we need to do in order to increase f as much as possible by going in a particular direction. Let's say a distance of 1, we need to follow this gradient, right? So we need to follow this vector. So what does it mean in this picture? Well, this says take a point xy, so somewhere over here, and in order to increase f as much as possible, move somewhere here, like that. So here what we're doing is we're moving xy in this direction, which is a direction in 2D. It's a direction on this plane. It's not actually the direction that points uphill on the surface plot, because this direction, it's in 3 dimensions, right? So it also has the z dimension. However, this does give us a starting point, because if we know that this is the direction in which we need to move xy, we can just deduce the direction in which z needs to move in order to actually stay on the surface plot and not kind of fly off it, right? So basically the question becomes, if we move xy by this much, how much does z move so that we stay on the surface plot? Okay? So all right, how do we determine that? Well, in order to determine that, what we need to do is we need to say, okay, so what's the effect of moving x by this much? And what's the effect of moving y by this much? And if we're not actually moving all that much, we can just add those effects together. So let's start. What's the effect of moving x by this amount? Well, in order to figure this out, what we need to do is we need to just compute the partial derivative of f with respect to x. So what we can say is that, okay, so df by dx at the point xy, what is that? Well, for a small h, this is just going to be f of x plus h, y minus f at xy divided by h. So this is just the definition of the partial derivative at xy. But this actually gives us a way to estimate the effect of the change in x on a change in f. Because what we can do is we can just say, okay, so what that means is that h times df by dx at this point xy is just equal to f of x plus h y minus f at xy. This, notice, is just the effect on f. So this is the effect on f, so on the value of f, of moving x by h. Okay? Because you move x by h, and this is how much f grows. So you just subtract the old value of f from the new value of f. Right? And that's equal to this. How can we use it? Well, we know that what we want to do is we want to move x by alpha times df by dx at xy. So this is going to be our h. In other words, the effect of changing x by this much is just going to be the h. So alpha times df by dx at xy times this guy, times df by dx at xy. So this is going to be the effect of moving x by this much, by alpha times df over dx at xy. So this is where the square, which confounds a lot of people, comes from. It's the h contains a df by dx at xy, and also we're multiplying it by the derivative, and this way what we get is we get the effect of moving x by this much on the f. So okay, now that we have that, we can move on